Alright, so now we want to talk about applications of some of this number theory. And I'm going to run through a few applications in this video, and then in class we're going to talk about cryptography, and we'll talk about that in a fair amount of detail, but we'll do it in the classroom probably on a Friday. So one application is what's called parity. And the idea of parity is pretty simple. Suppose you want to send a binary number, and let's say it's an 8-bit number. It's possible that one of these bits might get flipped if you're sending this over some sort of unreliable transmission system. For example, a phone line where you're using tones, the way we used to use modems. It's pretty easy for one of these bits to accidentally get flipped, and you might get something like this, where this bit here has changed from a 1 to a 0. And in the absence of any kind of check system, there's no way to know that that's happened. So early on, a really easy system was developed for checking to see if a single bit got flipped somewhere, and that was the idea of adding an extra bit, which we call a parity bit. And there were two kinds of parity, even and odd. So let's talk about even parity. The idea is we're going to add an extra bit here so that the number of ones is even. Now, the numbers in these 8 bits, we're sending an even number of ones. We're sending 4 ones. So we would set the parity bit to 0, so that the total number of ones in this 9-bit quantity is even. So when we send our data and it gets received like this with a bit that's flipped, the receiving side says, how many ones do I have? I've got 3 ones. That's an odd number. It says something went wrong. So that generates a parity error. And it would signal back to the sender, hey, I didn't get the message clearly, please resend it. Right? And this works for a single bit upset, and it even works if the parity bit itself is the bit that gets flipped, because you're guaranteed to notice if a single bit has a different value from what it should. The problem, of course, is that if 2 bits get flipped, right, then it looks like we got an even number of ones. The receiving system would say, okay, that's a good number, fine, and we've actually got 2 errors. Now, in an odd parity system, we make sure that the number of ones that are transmitted is always odd. So the number itself contains 4 ones. That's an even number. We would set the parity bit to be a 1. And this is particularly useful if something goes wrong and we start just receiving zeros. We're going to know immediately that's an error because we should have an odd number of ones in there. So that's one application of some of this. And the way we compute the parity bit, if we're doing even parity, we just add up all these digits and we calculated modulo 2. For odd parity, we take up all these digits, calculated modulo 2, and make sure that it's equal to 1. And so the parity bit would be 1 minus the sum of this modulo 2. So a little bit of number theory in there. Another application is hashing. And we'll talk about hashing a lot when we get to CSE 222. But basically it's a way to take a long string of information, say something like a name, and change it into a small integer typically, so that we can store that name in a short array. And this hash function is a combination of arithmetic operations, modulo operations, and so on. So we'll use some number theory when we talk about hashes. All right, 2 other applications I want to talk about, and these are other versions of error checking. One is these universal pricing codes. So pick up any product, and if you look at it, there's a UPC code somewhere on most every item that you'll find in a store. And I'm not going to pay attention to that 0 on the left. I'm going to write down these 10 digits and this 1 on the right. So this is 71662. 00816, and then a 1. So these are scanned by hand by automated systems. You run it over a scanner and it picks up the code. But it's possible that something could go wrong, and somewhere in this code a digit could be misinterpreted, right? These digits are coded by this pattern of bars. But what happens if one of these bars is incorrect somehow, right? So this code captures a series of pieces of information, including a product category, right? That's the 7, a manufacturer, which is 5 characters, and then a product itself. Sorry, I'm going to put the 0 in the front here. So the 0 is the product category, and then there's 5 digits for the manufacturer, and then 5 digits for the actual product from that manufacturer. And then there's this 1 at the end. Well, this 1 is what's called a check digit, and it's a number that can be generated from these 11 digits. And if any of these digits changes, you'll get a different check digit. Okay, so it's a way to ensure that this coding with these bars is done accurately. So so here's the way UPC works. Basically, we use a formula. So if we think of these as x1, x2, x3, and so on, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up through x11, we calculate 3 times x1 plus x2 plus 3x3 plus x4 plus 3x5 and so on, and we take that sum and we reduce it modulo 10, which is convenient because it means all we need to worry about is the last digit. And then if that sum is not equal to 0, we subtract from 10. And that'll give us a single digit. That should be our check digit. So this is basically 3 times the sum of the odd characters plus the sum of the even characters, mod 10. So let's just underline the odd characters, and let's multiply those by 3. So I'll just add these up: 0 plus 1 plus 6 plus 0 plus 8 plus 6. And I'm looking mod 10, so this is 6, and 8 is 14, that's 4, and 6 is 10, that's 0 and 1, so that's equal to 1. So 3 times that is equal to 3. And now I'm going to add up the even positioned digits. So I've drawn arrows there. So 7 plus 6 plus 2 plus 0 plus 1. 7 and 6 is 13. That's 3, 5, 6. That's equal to 6. And I'm going to add these two together. 3 plus 6 equals 9. That's not equal to 0. 10 minus 9 equals 1. That should be our check digit. And in fact, it is. So we know now that this code is, in fact, probably correct. Now, are there possibilities that there are errors in here and we still got a check digit of 1? Sure. 1/10 of all codes are going to give us a check digit of 1. But this will pick up any single error, and I think it picks up transpositions as well, because if you swap 2 digits, you're going to be multiplying the wrong one by 3 in most cases. Okay, so it's a pretty reliable code. So we'll play around with that in class. The other one we'll play around with is ISBN codes. And that's this code that you see on textbooks typically, where there's this big long code down here, this code up here, ISBN, and this 7 over here is a check digit on the other digits in the ISBN code. And ISBNs are very reliable. They catch single character errors and they catch all transpositions. And it's just a way to sort of validate that the number you're typing in is valid. Credit card numbers have check digits inside. You can't type any 16 digits and have it be a valid Visa number. It's got to have certain properties. And from those properties you can tell if it's an invalid number. Of course, it could be invalid and still have those properties, but it's sort of a first order test. Alright, so we'll explore some of this in some homework problems.